Hey everyone, welcome back to MD-Sim 360, the Molecular Dynamics Masterclass. In this video, we're taking the next step in our MD simulation journey, the NPT equilibration step. This phase stabilizes pressure and temperature while allowing the system's volume to adjust automatically, bringing us even closer to real-world conditions. Previously, we covered the NVT step, where we equilibrated temperature at a fixed volume. Now, with NPT, we introduce another layer of realism by allowing volume fluctuations while maintaining stable pressure and temperature. This step ensures the system reaches a fully thermodynamically stable state. It's also the final equilibration phase before the production run, where we simulate the system without constraints, just like in nature. At this stage, we need to verify that all graphs and system properties indicate full equilibration. Once confirmed, we can proceed confidently to the next phase. Now, let's break down the key parameters for NPT equilibration. The first four are the same as in the NVT step, so I'll quickly recap them. First, we have neighbor list update frequency. This tells GROMACS how often to update the neighbor list. Here, we've set it to 20, meaning after every 20 steps, the list gets updated to ensure interactions are correctly computed. Next is the neighbor list cutoff radius. This defines the distance within which atoms are considered neighbors. Then, we have the van der Waals interaction cutoff. This cutoff ensures that only interactions within a specific distance are considered, making the simulation both accurate and computationally efficient. Similarly, we have the Coulomb interaction cutoff, which sets the radius where electrostatic forces interact. Now, let's talk about temperature and pressure coupling in the NPT step. First, we have temperature coupling, which helps maintain a stable system temperature. Just like in the NVT step, we'll be using the same thermostat to regulate temperature. The key parameters here are the time constant, which determines how quickly temperature fluctuations are corrected, the reference temperature, the target temperature we want to maintain. Now, the major addition in this step is pressure coupling. In NVT, we only controlled temperature. But in NPT, we also regulate pressure to make the simulation more realistic. For this, we use Berenson's barostat, a reliable method for stabilizing pressure. It works by gradually adjusting the system's volume to reach the target pressure. In our case, we've set the reference pressure to 1 bar, so the system will continuously adjust its volume to maintain this pressure. Since volume is directly linked to atomic velocities, all of these factors, temperature, pressure, and volume, work together in this step to bring our system closer to real-world conditions. To keep the system stable, we also use a time constant of 2 picoseconds. This helps adjust the reference temperature every 2 picoseconds. While we could use 1 picosecond, 2 works better here as it minimizes frequent changes, which is important for this complex system. Every 2 picoseconds, the coupling algorithm will also adjust the system's pressure. Another crucial parameter is system compressibility, which is currently set to 0.45 bar inverse. This parameter defines how the system responds when pressure is applied. Essentially, we're applying pressure to the system, and the compressibility value indicates how much the system resists this compression. It tells us the system's response to pressure changes. Additionally, we've imposed a constraint on the bond length. This ensures the bond lengths closely match those found in real-world environments, helping preserve the accuracy of the simulation. Next, the final parameters remain the same as those in the NVT step. Now, let's proceed with the NPT step by clicking the Run NPT button. As you can see, the NPT step is now running. It will take a bit more time than the NVT step, so let's wait for it to finish. Now we have the results from the NPT step. As you can see, All the graphs are displayed here. These graphs give us valuable insights into how the system has stabilized after the NPT step. Let's go through each of them one by one. As you can see, the potential energy has fluctuated considerably, but has ultimately stabilized. Next, we have the total energy. It fluctuated initially, but eventually stabilized. Next, we have the three parameters, varial XX, Y, Y, and ZZ, which represent the pressure tensor components. The XX component reflects the behavior along the x-axis and helps us observe the isotropic behavior of the system. What we need to observe here is that, at the beginning, there will be significant fluctuations. The goal is to ensure that, by the end of the process, these fluctuations have been minimized and the system reaches a stable state. The same observation applies to the YY. And same observation applies to varial ZZ. In this case, although the fluctuations may seem quite high, the average value remains relatively constant over time. Additionally, we can see that this parameter also stays within the acceptable variable range, ensuring stability in the system. Now, we once again observe the Coulomb's short-range interactions, then followed by the Leonard-Jones short-range interactions. Looking at the Leonard-Jones short-range interactions specifically, we can notice that they show greater variation compared to the previous NVT stage. From this observation, we can infer that during the NPT step, there is slightly more variance in these interactions. However, despite this increased variance, the system overall appears to be highly stabilized. Given this stability, let's move on to the next step. Finally, we have the positional restraint. Here as well, we can observe that the values remain within the acceptable range. There is minimal variation, indicating that the system is maintaining stability. Since everything is stable, we can proceed with the energy equilibration step. Next, we will move on to the actual production phase, which is the most crucial step in this entire process.